Hello and welcome to this lecture on implementing list decoders for polar codes. Okay. So I gave a couple of we did one lecture earlier on how to do list decoding. I described the whole philosophy from a high level, the path metrics and decision metric, and adding the decision metric to the path metric and comparing path metrics and having a list size of 4, picking the least path metrics. All of that we described earlier. And I also described to you the block diagram of how a list decoder works and how the CRC insertion is important. Okay, so the list decoder is going to put out a list of code words. From that, how do you pick the code word that is a valid code word? You use the CRC check. Okay, so in this lecture, we will see how to implement that. We will take our existing successive cancellation decoder and add the list decoding components. You will see it's sort of okay, it's easy to do in MATLAB at least. You simply, instead of having one decoder, you will have multiple decoders, and once again we will not be doing this efficiently at all. We will just do a decoder to get it to work, and we will think about adding efficiency and other things maybe later on, and in fact I will leave it to you as your work, how to improve the efficiency in these decoders. Okay, for now let's just look at how the implementation goes. Okay. So the first step, like I mentioned, is to add CRC. Okay, without CRC, the list decoding is not going to work. It doesn't make sense at all. So you saw in the LDPC code also, actually in the standard there is a CRC, but we never implemented it. It's not needed in the LDPC code. But in this case, CRC is critical for the list decoder. Okay, so here is what I've done with the CRC. So you notice quite a few things have changed. I've made A as the number of actual message bits, and CRCL is the number of CRC bits. Okay, and K, which is the message dimension of the code, is A plus CRCL. So 500 plus 11 is 511. Okay, and for the CRC comes with a polynomial, and the polynomial is clearly defined in the standard. That's the polynomial for you. Okay, so if you write it out as a polynomial, okay, so the CRC for length equals 11, the polynomial as defined in the standard, it's right there. Okay, 1 1 1 0 0 0 1. So this is x bar 11 plus x bar 10 plus x bar 9 8 7 6 x bar 5. Okay, the polynomial is x power 11 plus x power 10 plus x power 9 plus x power 5 plus 1. Okay, so this is the polynomial. Okay, and the way in which you do CRC, we are not going to describe the ideas of CRC and all that in this class, but we will see how to implement it in MATLAB at least. So this is the CRC polynomial. You need this. So if you choose to do a CRC of a different length, let's say length 16 or something, then okay, so if you choose to do a polynomial CRC of a longer length, say 16 or 24, these are also possible, then you have to change your CRC polynomial. Okay, you change it to something else. Okay, all right. So now the next thing I put, so you see the quantization, all of that is fine. Next thing I have is list size. Okay, so I'm picking that as 4. You might want to have 8 maybe later on if you want more performance, but 4 is a good enough number and seems like a reasonable number. And notice here rate becomes A by n. Okay, it's not K by n anymore, it's A by n. The reason is CRC bits are actually parity bits, they are not message bits, and we are using those parity bits in the decoding in the list decoder. So the rate is A by n, and that's something important as well. Okay, so you should capture that as well. Okay, so once you do that, other things don't change too much, except so let's focus on the CRC computation. Okay, so you have the message that gets generated. Remember, I'm generating only A messages now, not K. And then I do a division. You have to divide one polynomial by another. So what I'm doing here is setting up those polynomials. Okay, and I'm using this function gfdconvolve, which is available in MATLAB. It's also available in Octave. So if through some toolboxes, so you can this command will work. So it will divide the first polynomial in binary by this other polynomial. The reason why we do this flipping, okay, so you saw the flipping even in the CRC G definition if you saw it earlier. So even here I flipped. The reason is this gfdconvolve function uses values in increasing powers. So you have to do this flipping to make sure that the increasing powers of the polynomial get correctly reflected. The zeros I put here is the remainder. Okay, the remainder will come and occupy the 0 positions, and this is just the message flipped so that the polynomial becomes the correct degree, and then you have that down here. Okay, so you find the remainder. The quotient is actually not very relevant to us. The remainder is what matters, and the remainder gets added to the CRC part. Okay, so the message comes as it is, and then you will take the remainder and 0, and I've done flip LR as well. Okay, so that's okay. So that the remainder, which is again in increasing powers, becomes in decreasing powers. Okay, so this is how it is done. Okay, so this is described in the standard as well, and the only thing to note is I use this DFGF deconvol to do the division of polynomials. Okay, so polynomial division is not very difficult to write. In case you don't find it, it's easy to write polynomial division, but nevertheless we use this function to make our job easier. Okay, so you have message, and then you have message plus CRC. This will be k bits. Okay, so this will be this, you can see I've made it equal to CRCL. Okay, the length I've added enough zeros to make sure that the overall length is CRCL, and this will be k bits. Okay, so maybe I should write that down, and then after that I just encode CRC. So message CRC is what gets assigned as the U value. Okay, so there's something to take note of. And then after there's no major change as far as the encoding is concerned, and modulation and quantization. Then comes the big change in the SE decoders. Okay, so you need NL decoders, right? So how many ever list size you want, that many decoders you need. Okay, so these LLR values. Okay, so previously I think I had it as capital L. I have now changed it as LLR. It's just a change in the notation. These LLR values will not just be n plus 1 comma n. So if you go look at the SE decoder, this is just the successive cancellation decoder. If you look at the successive cancellation decoder, this L was just n plus 1 comma n. What have I done in the list decoder? So if you notice, this first tab I have is the SC decoder. The last tab that I have is the SC list decoder. In the list decoder, this LLR values, there is 3 dimensions in the array. Okay, the first NL gets added. NL comma n plus 1 comma n. For every decoder, I need a new array, a different array. Okay, so we need NL of these U caps also. Okay, and then I need the path metric. Path metric I'm calling as PML. So this path metric wasn't there before. We need it now. If you notice, I'm initializing the path metrics. There are NL of them, and all of them I'm initializing to infinity. Okay, and then I'm setting the first alone to 0. Okay, so which means initially only one decoder is active. So if the path metric is infinity, it means it's not going to be considered by anything. Okay, so infinity is just a value I use in MATLAB. You can use some other value if you don't like it. Okay, so that's the path metric for you. Okay, so this node state vector is actually common to all the decoders. Okay, so you don't need to maintain multiple values for node state vector. It's the same thing. All the decoders traverse at the same time. Okay, they are synchronized in that fashion. Okay, so initialization at the root. Now previously we did only for one decoder, so the only one value got initialized. Now we have to repeat it for NL times. Okay, so all the beliefs of all the decoders are initialized. Okay, and then after that the decoder actually proceeds in the same way. So the node and the depth, and moving left down, and then going back up, and then going right, doing the F operation, doing the G operation, doing the U operation to go up. All of them are the same. Okay, except that you have to repeat it for all the decoders. Okay, so let me start with the L operation. Okay, right, this doing the step L and going to the left child. So if you notice, nothing much has changed except that this command, this ln, was not using the squeeze before, but now I'm doing the squeeze. So if you look at it, LLR of colon, which means I take the values from all the decoders, not just the one decoder, all the NL decoders, and then I squeeze out that the dimension. The depth plus 1 is just a single dimension, so I squeeze it out, so I get a 2-dimensional array. This ln will be a 2-dimensional array. Okay, and then I split it into A and B, and then everything else is the same, and then I assign the F value back into the original array. Okay, so that's all. So instead of doing it for one decoder, the same operation I repeat for NL decoders at the same time. Okay, same thing with step R also. Nothing changes in step R. Same way we squeeze, and we get from the 3-dimensional array, we go to a 2-dimensional array. Okay, to get all the values for a particular depth. Then you find A, B. Same thing with U cap n. Nothing changes except that you're doing the same operations for 4 decoders. Okay, and same thing with step U also. Okay, the step U that goes to parent, nothing much changes. You do it for all 4 decoders. Okay, the only significant change is in the decision. Okay, when depth is n, Okay, when it is a leaf, you need to make decisions, and there the list decoder has a lot of change. Every time you make a decision, you have to update the path metric. You will get 8 path metrics. You have to choose the best 4 out of the 8 path metrics and throw away and do some rearrangement in the decoders. Okay, so that requires some effort. Okay, and there is a change there, and let me talk about it first. First is the decision metric. Okay, this is the decision metric for the 4 decoders, and first you check if it is frozen. If it is frozen, things are easy. Okay, if it's frozen, there is no need to look at both decisions. If you remember from the lecture, if the bit is frozen, you simply decide everything is 1, everything is 0, but you update the path metric. This is important. Okay, path metric is updated. If the path metric is negative, the absolute value gets added. Okay, this piece of code does that for you. Okay, absolute value dot into dm less than 0. So if actually the dm is negative, it will get the absolute value will get added to the path metric. Okay, and then after that, in case it's not frozen, you have to make decisions. Okay, I'm first deciding according to the decision metric. This DEC is a decision as per the decision metric. Okay, and now what I do is in PM2, not only do I consider the decision metric, I also consider the opposite decision, which will make the path metric increase by absolute value of dm. Okay, so that's what I put here in PM2. First NL are as per dm, next NL are opposite of decision metric. Okay, so the decision you made in the first NL positions is according to the decision metric. The next NL, in the 8 decoders you are considering, the first 4 decoders, the decisions you made were as per the decision metric. The next 4, it is opposite to that. Okay, so there are multiple ways to do it. I am doing it in this fashion. Okay, and then I do these adjustments. Okay, so find out those that survive. So this is the important step. This is the sorting step. Okay, so this uses min k. What is min k? If you have an array, min k will give you the least 4 elements from the array. Okay, so remember this PM is all positive values, so you don't need to take absolute value anymore. So this min k will give you the least k values from an array. So this PM2 has 2 times NL length. Okay, 2 times NL. If NL is 4, it has length 8, out of which I will take the least 4. Okay, so you get the new PML, okay, which is the least 4, and also the positions of the new PML is in pos. Okay, which are the least 4? You had 8 values. Some of them could be in 1 to 4, some of them could be in 5 to 8 also. So which came into the least 4? That is captured in pos. Okay, so I need to know which of the decisions are that survive. Okay, the decisions that survive are in pos. Okay, which survive and they are opposite of dm, that I need to know. Okay, and then I need to subtract this NL to get the actual indices. Okay, and then permute the decisions as per that, and then invert the decisions when the decision is opposite of dm. So these are just routine operations. We will run it once and I will show you how this is working. Okay, and then I rearrange my decoder states. Okay, so basically I delete the decoders that are not valid and keep the decoders that are valid, and then assign this to decision. Okay, so this little piece of code actually implements the list stage. Okay, so expanding the list from 4 to 8 and then contracting it again back to 4. Okay, so you go to 8, you consider both decisions when the bit is not frozen, arrange the path metrics, pick the best 4 of the path metric, okay, and then do the adjustments. So the adjustments are a little bit complicated. I will let you look at the code and think about it. The code is there with you. If you run it once or twice, you will see how the code works, and you will understand what I mean. Okay, so it's a little bit involved. I don't want to go into great detail on the code. Okay, but this part implements exactly that. Okay, so if you have a version of MATLAB or Octave, I'll let you run it for a while with some small length maybe, and then look at what this piece of code is doing, and then you will learn a little bit more about how this is doing. And clearly this is not the only way to do it. There are multiple ways to implement this. If you have a better way, you're welcome to implement this as well. Okay, so this is the implementation of the list decoder. Please look at this part of the code and try to see if this is correct, or if I made any mistakes, or if you think you can improve this in a nice way. Okay, so that's the implementation of the list decoder. Okay, so now what I want to do is maybe run this once. I will run it once. Now when you run it, it's good to stop at a particular place. Now MATLAB's debugger allows all these kind of nice and simple conditions to make you stop somewhere. So I'll stop at some point, let us say 250. So, at the 250th node I want to stop. So, I will set a conditional breakpoint there and then I will run it. Okay. How many blocks I am running? I think it's enough if I run one block. Okay. Let me save, I'll run. Okay. Brief warning about min k. So, I believe MATLAB introduced this in 2018 onwards. So, in case you have an older version, you have to write your own min k. So, min k is not very hard to write. Here is a simple version. Min k of x comma k is simply sort it and take the first k. Okay. So, this is actually not very efficient. There is a algorithm which will find the minimum k without sorting the whole list. But anyway, so for quick and dirty implementation, this is good. Okay. I have set my breakpoint here and now I am going to run this. So, we can implement our own version of min k. You need to return the minimum k elements and where they are also. Okay. So, that requires a little bit of coding and you can do that with sort. Sorts it in ascending order. You pick the first k and return it, and pick the first k positions and return it. Okay. So, this will should work, and this is your own min k, and you can use MATLAB's min k as well. It's probably definitely more efficient. If you have 2018b or later, I think that will work. Okay. So, let us run this. So, it has worked and it has gone up to node of node will be 250 like I said. So, let us look at so what happens at this point. So, it is interesting to look at the path metrics. I am sorry, PML I think was the path metric, 118, 149, 149, 149. This is the path metric at this point. Okay. And you find the decision metrics and see if it's frozen, it's not frozen. Okay. So, you went into the decision. Okay. So, let us look at what the decision metric was, 31 minus 6, 31, 0. Okay. So, that is the decision metric at this point. Okay. You look at the decisions as per the decision metric, you will see this will be 0, 1, 0, 0. Okay. And then you look at the PM2. Okay, so notice what PM2 is. Okay, it is the path metric if you decide as per the decision metric, and the path metrics if you decide opposite to the decision metric. Okay, so you add the DM absolute value. Okay, and then you sort it. Okay, your min k. Okay, so if you do the min k, you get the new PML, which is you see that 149. Is the one that is one out. There is nothing, no major churn that has happened here, and pause is just 1, 2, 3, 4. So, everything is easy. So, maybe what and you can see how this is done. So, this is not very instructive. So, maybe I'll set up a breakpoint here and then continue to get to the next one. So, we see PML. It's the same thing, but hopefully the decision metric is a little bit more interesting. Let us see if the pause became a bit more interesting. No, it's again 1, 2, 3, 4. So, if it's just 1, 2, 3, 4, then you're not doing a lot of sorting and moving around. It's not very nice. So, maybe I'll continue for a few more things and then step in and see. Okay, I think maybe we are in luck. Okay. So, let us look at, okay. So, here is an interesting situation where pause became 1, 2, 5, 3. So, your PML and PM2 look at. So, this was the PM2 188, 219, 223, all these things. So, when you sorted, you got 188 first and then 219, another 219 and then 223. So, if you look at the positions, 5 got added. So, you got 1, 2, 3, but 5 got added. So, you made a decision opposite to the decision metric. So, when you do that, you have to find the places where this pause 1 happened. So, pause 1 is will indicate to you the positions where decisions opposite to the DM was done. This was in the third position. So, you get 0, 0, 1, 0, and those alone you have to subtract NL, so that you get back pause as remaining one. So, what happens here is the first decoder had both decisions surviving. Okay, first decoder's decision as per its decision metric and against its decision metric also survived. Okay, and then 2 and 3 had decisions as per their decision metric surviving. Okay, and then you did that, and then see, remember, decision was according to the decision metric. So now I have to permute it as well, because some of the fourth decoder, for instance, is not even there. So that needs to go, and then I have to flip the pos one. Okay, after that you just continue as it is. Okay, so that was one example to show you how this decision happens. And then what do you do after everything is done is you have to check your CRC. So let me just run to cursor here. I've come here, all my decoding is complete. I am looking at the candidates. Okay, so I am taking all the candidates. You will have NL candidates, all of them will be in message cap L. Okay, and then you have to see which candidate is to be outputted. You go through all the candidates, okay, and then you do the division again to check which CRC is satisfied or not. So let's go through this. So I'm going and checking if the CRC is satisfied or not. If R1 is 0, CRC is satisfied and it passes. Yes, it passes. So you're done. Okay, so it might happen that this R1 is not 0 also, but in most cases the CRC will pass. Okay, and you get through and you get the decoder. Okay, so hopefully that showed you how the decoder works, and maybe you can for instance, if you're curious to see what the Cout is, you can print Cout. Sorry, print doesn't work here. So you can display Cout and then run the decoder for a little while, and you'll see whether or not other decisions are getting done here. So let me adjust the EB over N naught to something like, say, 1.5, and then do 100 blocks. Okay, and remember, I am outputting the Cout, which candidate code word got chosen. Okay, so if you run it, so you see one comes quite often, most of the time. There was a 2. Okay, the second candidate got chosen there. Once in a while, we don't expect we always expect the least path metric candidate to win, but once in a while you will get something lower also. Okay, so that can happen. Maybe you'll go to a lower SNR. Maybe you'll see more of it. Okay, so most of the time the best path metric wins. Okay, once in a while you get the second path metric also winning. Okay, very rarely. Okay, here you got one more. Here you got one more. Here you got 3. Okay, so once in a while when the decoder happens, the second or third candidate code word passes the CRC and the other thing doesn't pass. Okay, so if you want to do repeat the simulation that we had, remember this is roughly rate half, and we saw 2 dB was the number where the LDPC code was giving you 0 errors for 100 code words. Let me stop the display of the Cout. This is not needed anymore. Okay, so let's just see if 2 dB for 100 code words for rate half for the polar code list decoder with 4, how does that perform? Does it give you 0 or not? It will give you something better than the SC decoder at 2 dB. That gave about 12 errors out of 100, if I remember correctly. This should give you something better. Let's see. So it gives you 0. Okay, so you see in these 100 code words, the list decoder decoded and gave you 0. If you actually run for the SC decoder at 2 dB, which we did a little while ago, 2 dB with 100 blocks, you will see this will give you some errors. It won't give you 0. It give you 14 errors out of 100. So you see there is an improvement in the list decoder. Okay, so we see that the list decoder really improves in performance by that little bit to make it comparable maybe with the other decoders. So in an ensuing lecture, the final lecture possibly of this course, we will compare this rate half length 1000 code between LDPC and Polar, and then run simulations and compute, show you the simulation results, and I'll show you how you can compare these 3 codes and decoders and make a nice plot of BER versus EB over N naught and make a fair comparison. Okay, with that we'll conclude this course. Okay, thank you very much.